Hey guys. All right, everybody, open up an e-backpack. I put a class assignment for today with the part 3 notes for chapter 6. So go ahead and take a second. You're going to add them in to your existing notes, and we're going to round out the chapter today. Okay, so today we're going to take the next step in understanding topography and how we gather information about what Earth's surface actually looks like. But now we're going to take it in the direction of technology. So up here on the screen, you see a nice picture of a satellite, and we're going to try to understand a little bit better how satellites are being used to give us information. So Earth's only natural satellite, we said, was the moon, but thanks to NASA and SpaceX and all these different companies, we've been able to put man-made satellites that are bouncing information back and forth between receivers and units down here on Earth, and then these satellites that we actually put into orbit. So a satellite, by definition, is, and I'm just going to zoom in here so that the people in the back can see nicely. A satellite is a small object that orbits a larger object. So what we're talking about here are man-made satellites, and we use them for tracking hurricanes and storms. GPS is a big one, right? When we say GPS, that stands for Global Positioning System. Now, the interaction with us and our cell phones, and we're like, oh, let me put on my GPS. Are you actually bouncing off of a satellite when you do that? Or are you bouncing off cell towers? That's a topic we're going to get into today, and there's actually a link for you guys to better understand some of that information. And then we mentioned the other day that you can use Google Earth to get images of Earth's surface, where you can actually go in there and you can take a look at your house. You can take a look. Maybe you're thinking about college in a couple years. You're like, what is that area going to look like? Well, you can punch these different places in. You can see the lay of the land and get a sense of what's around. Myself, I like to do that if I'm going to try and follow a new set of directions. I might punch it in there and I can actually see landmarks that I'd be looking for when I'm driving. So you guys kind of get the sense of how these satellites are being used. But there's actually two different types of satellites. We have geostationary orbiting satellites, and we have polar orbiting satellites. Now let's break down the word geostationary just for a second. Geo meaning Earth, stationary as in fixed or not moving. Now, if there was a satellite that was orbiting the Earth, obviously it has to be moving, but to us it appears to be stationary because at a distance, get this, 36,000 kilometers. I'll say it again, 36,000 kilometers. At that distance, they set that satellite in motion at a speed at which it can appear to be fixed in our sky. So it's moving so fast, 36,000 kilometers away, that when you look out, you just see a solid dot in the sky. You wouldn't even notice a geostationary satellite because it would just blend in with other stars. So please don't go home tonight and go, oh, I'm going to spend the evening trying to find one. Good luck. All right? But that is one of only two types, as I said before, because there's another fun type of satellite called a polar orbiting satellite. And those are the really fun ones because those you can actually see moving across the sky. They complete their orbit around the Earth every 90 minutes. So when we go up to Founders Hollow, go up onto Tabor, sometimes on a nice clear night, you can actually see one of these steady dots just move across the sky. The International Space Station actually is polar orbiting. So if you ever watch footage from the International Space Station, you'll see that the Earth below is moving really fast. Or more so, the International Space Station is moving really fast over the Earth. Okay, so we mentioned both types. Now, what are they good for? Well, when we talk about the geostationary, it's going to be really useful for weather and for communication. So try to paint this picture in your mind that you're here fixed on Earth and you want to be able to communicate with the satellite. Well, if they can put that satellite in one spot and and that you can continually bounce off of that one satellite or a cluster of satellites that are in a fixed position in relation to the Earth, well, now you can develop communication between them. And that's exactly what a geostationary satellite is going to be there for. Now, polar orbiting gets a little more interesting. As I said before, it's going to make its lap all the way around the Earth every 90 minutes. So it's actually very helpful if you want data pertaining to Earth's surface. So if you want to map Earth's surface, if let's say you want to do reconnaissance of things going on Earth's surface, you're getting a continual feed. You're seeing the full Earth, full 360 view every 90 minutes. So it would be a little more easy to pick up on changes on Earth's surface. All right, so I'm just going to slide over real quick, zoom in, and you guys can see the difference between the two types of satellites. Right? One is rather close to the Earth, the other one very, very far away, and again, geostationary. It has to be set at that 36,000 kilometer distance in order for it to sync in its orbit with us. All right, so let's bring this back. Ooh, too much. And let's talk about the Global Positioning System. So, Global Positioning System, or GPS, when we're talking about using satellites, will determine one's location by sending a signal out, a radio signal out, and then it being bounced back. And a computer is actually able to calculate the difference in time, sending it out, coming back, to then convert that into a distance. Now, if you notice in that picture, there were 4 satellites. So go ahead and take a look in your notes. And you need to fill in the GPS receiver detects radio signals from at least 4 nearby GPS satellites. Now that's how a satellite GPS would work. Now, if you recall, we also talked about the idea of triangulation. And triangulation requires that you have 3 points. So initially, when the military came out with GPS, which really is where satellite GPS came from, there were a whole bank of different satellites, but they only needed 3 in order to determine their location. The 4th, so branching off from triangulation, the 4th is there for confirmation, right? You want to know definitively where you are. And if you think about it from a military perspective, it'd probably be really good to know exactly where you are if you're calling in ordnance, or if you have to go maybe pick up a crew that their plane's gone down and now you need to send a team in a rapid response. So that's where that 4th one comes in. But as I said earlier, we're not always using GPS with satellites when we're actually on our phone or when we're in our car. There are a lot of different ways to figure out one's location. So that's where the idea of triangulation now comes in, and the idea of cell towers. So just to give you some real-time data, I was up in Vermont over the summer, and We were trying to hike on a particular trail and kind of got ourselves a little lost, off track, trying to find a cell signal and also trying to get my GPS to work. My phone doesn't bounce off a satellite. If I had a satellite phone, wouldn't have been an issue. Instead, I'm moving around trying to find my location, and we ended up getting in the car at one point and changing our location just to try and find a cell tower that we could ping off of, right? Because I could walk around, I can hold my phone up toward the sky all afternoon. It's not bouncing off the satellites that are above me. It's looking for a cell tower. All right. Anyway, you guys are like, that's great. We really don't care about your hiking adventures. It's okay. I don't take it personally. Now, on to something you guys do care about. And you're sitting there going, the screen says geographic information systems. You might not initially think, well, what do I care about a map that has data crammed into it? But in fact, marketing loves this type of map, because what they do is they take information like, I don't know, when was the last time you saw a Verizon ad and it says, oh, Verizon's service covers this much of the US, and it's like all red, and then they show that same map with information about T-Mobile or AT&T or Sprint or whatever other company they want to compare themselves to. That's using geographic information and blending it into the computer system. Here you can see the average wind speed, and that information now they color code it and can put that into the US. Now notice this little area right down the center, and I'm just going to circle it real quick. Right, this whole area over in here is going to be super, super important later on when we talk about tornadoes, right? So we'll get into that in the third trimester. But where else do you guys see geographic information systems? You see them when you were checking out politics maybe a couple weeks ago, and as the numbers were coming in from the different elections and races, hopefully you guys paid attention to some of that, they can break it down town by town, county by county. With the presidential election a couple years ago, they could tell you, okay, so the state went this way, but county by county, how many people voted that way? And what was really interesting is they were able to zoom in and then take the statistics on top of that. So they could click on a random county in the middle of Ohio, and it could tell you how many times that particular county went Democrat or Republican. So that's a use for this satellite information and blending data that's been collected together. Now, I might have gotten ahead of myself. So, computers have improved how maps are made and have increased the amount of information that can be displayed. I figured if I gave you examples now, that note makes a little more sense. Why do we actually care about computer-generated maps? Well, it's all about information, right? Whether we're talking about a map of the mall, whether we're talking about a map of the subway system, or here we're talking about merging statistics and data with an actual physical map, we're constantly trying to relay information to people. And computers make it really, really easy to cram a lot of information accurately into a map. All right. So that pretty much rounds out our regular notes. Now up here, you guys have some additional notes, some rules to consider when you're working with contour lines, as we were working on Friday. I want you guys to be able to work through that second packet that I had given you. So I'm going to take a quick second, review some of those rules, and then we're going to do a quick exercise together, and you guys are going to spend the rest of the period working on that second packet. So, Rules to determine contour intervals. As I said the other day, I want you to find two labeled contour lines, and index contours are always labeled. All right. So, if you recall from our lesson the other day, we had a contour line, contour line, contour line, contour line, contour line, and contour line. And then one was 1,000 and the other one was 1,500. And we wanted to know what the contour interval there was. Well, you would do 1,500 minus 1,000. Let's make them both meters. And then let's divide, count the spaces, right? 1, 2, 3, 4, 5 spaces. And you guys can see real quickly that that ends up being 100 meters for your contour interval. Hopefully that's just a review for most of you when you're like, great, he's saying this again. Don't worry, we're going to practice with that in a second. But sometimes we come up on a situation where we have concentric circles going in the case of this particular type of contour setup. And initially you're like, okay, no big deal, right? I have my 10, my 20, my 30, my 40. On the inside over here, we'd expect that to be a 50. And I'm just going to highlight where the 50 would be. Right in there. That little circle would be a 50. And just in case you're still not really grasping the idea of what contour lines are, this particular image shows you what each one of those lines represent. So I'm hoping that helps some of you guys when you go back to study. Moving down, sometimes we have hatched contour lines. Right? And that's what this whole area over in here is supposed to be showing you. Right? So that contour line hatches, it looks like the little hairs growing off of it, and they point in toward the direction that the ground is actually descending. So these are hatched lines or depression contours. Now the trick with depression contours is that depression contour always equals the previous lower contour line. So we were at 1,000 in this image, then it went to 1,200 feet, then you hit a depression contour that has to be 1,200 as well before it goes down to 1,000. And I particularly like this image because it shows you can go all the way up to almost the next contour line, right? You could be 1, 2, 3 feet shy of that 1,400 contour. It's still going to be marked that as a 1,200 contour when it starts going back down. So if that idea is not resonating right now, it's okay. We can talk about it tomorrow when I'm in class. But I wanted to take a second and point that out because it might be helpful when we do this next exercise. So I'm going to fix the screen. Stand by. All right. So determining the value of depression contours, determine the outer ring. And the outer ring is equal to the previous low valued contour line. All right, so let's put this into practice. Here is a little practice exercise or check on learning. So I want you guys to take a second and try and work through the contour interval for each one and then determine the value of x. So I'm going to give you 1 minute. The clock starts now. I know for some of you right now this is a little awkward, but keep going. Get her done. All right, so I give you actually a little bit more time than I needed to. Let's take a look. The first one here we have 100, 200. Count the number of spaces in between. 1, 2, 3, 4, 5. So that should be a contour interval of 20. I'm just going to call them meters because I want to give it a unit. If you called it meters or feet, you're good to go. And that means that x is at an elevation of 180 meters. The next one. Now rather than 100 to 200, I have 1,000 to 2,000. And again, I have 1, 2, 3, 4, 5 spaces. So that means that my contour interval now becomes 200 meters. And my value for x becomes 1,400 meters. Now, I just want to pause and say if you're not getting it, that's okay. Come see me tomorrow morning and I will be more than happy to help you with this, or let me know at the start of class tomorrow and I will try to help you. In the meantime, try to stay with me as I go through the next one. Here we have an elevation of 5 and then this says 20. So how many spaces do I have in between? 1, 2, 3. 20 minus 5 is 15 divided by 3. That means my contour interval, in fact, is 5. But what is the elevation of x? X is above 20. So it has to be some number between 21 and 24. So today I'm going to go highest possible elevation. I'm going to say 24 meters. If you said that it was 21, 22, 23, or 24, you are correct. Let's move right along. 1,000, the next one says, labeled is 1,200. Over here, I have 1, 2 spaces, so it's an easy 100 meter contour interval, and therefore 1,200, 13, 1,400 is my value for x. So far, so good. Now it's time to try a depression contour. But luckily for you, the rule really isn't changing. Because this is 25, that's 45, it's a difference of 20. And then I have a 1, 2, 3, 4 space. So 20 divided by 4 is, very good, 5 meters. And my x is probably equal to 35 meters. Not probably, definitely is. All right, and over here we have 5,000 to 4,000. 1, 2, 3, 4, 5. And again, 200 meters. Contour interval, for the contour interval, and the value of x is 4,400 meters. I hope you guys are pretty comfortable with that at this point. Don't worry, there's plenty of practice in that exercise that I have for you. But wait, there's more. Over the weekend, I left you a video that had a tutorial link for how to make topographic profiles. So if you haven't watched that and you're really not understanding topographic profiles, I suggest you go back and watch it. Otherwise, you can follow some of these tips that I give you here. And then on this page, to better understand how to transfer those points and draw a topographic profile. So at this point, please take the rest of class to work on the topographic profile and topographic map worksheets that I gave you on Friday. There were two. Finish up if you need the one that we started on Friday and then transition over to the other one. It's a lot of really good practice. You'll get to finish whatever you haven't done for homework tonight. So have fun, guys. And to the teacher that's covering my class, thank you so much for your time today. Have a great day, guys.